Hello? Good morning to all of you. I would like to start the lesson. I know that there are only around 5 students currently streamed on. Um, for me, that's not gonna be a problem. I will still do the lesson. Mainly, you can actually see the lesson after it's done. It doesn't really matter as long as the lesson is actually streamed and you can do this later. Unfortunately for me, I think it's a bit disrespectful not to actually see it live. Now, what we're going to be doing, because I found these slides have been proposed to be used by Professor Sinagra himself. These are the slides that come with the new Valhart. Not sure if you have the 8th edition, but these are the slides for the 8th edition. So this chapter will cover chapter 22. Now chapter 22 is going to be what we're going to say as phenols and its derivatives. Now, can you hear me? Can someone confirm that I'm being heard and that the sound is correct so that I can move on? Brilliant. Now, unfortunately, between last lesson and today, I have been sick, quite sick actually. I had a massive fever, so I did not send you any questions. But I have prepared a couple of questions. There are some tough questions, and I will be sending them just after the lesson. So by 11, you're gonna have 2, 3 questions that you can work out. These questions, the way we're gonna be doing them is this. We'll find some time where we can actually have a live session. Shouldn't be long, 15, 20, 30 minutes maybe, where you can send me your answers on the Facebook group or email, and I will discuss those answers together using my board. This way, we can ensure that you have a good idea of what needs to be done and a good idea of how to use these mechanisms. Remember, these mechanisms normally are not part of one big system. These mechanisms, they follow each other. So it's not one mechanism so that then you can do another one. It's one mechanism and that compound might actually be stable and stay as the final product, or something else can happen. But we'll discuss this later on when we have a tutorial. I'm just telling you that today I'm sending you a few questions where you can just start working out. So, what is a resonance structure? A resonance structure you have discussed as a structure that has 3 or more adjacent p orbitals. Resonance structures tend to decrease energies, and this decrease in energy is brilliant because, of course, you can have different resonance forms, and you can have the movement of positive, negative, and radical charges. This movement allows for stabilization of a molecule, and this can only happen with the overlap of p orbitals. So, here, whatever hybridization we have, you need to have free p orbitals. If you don't have a free p orbital, this will not happen. We have two systems today. We have the allyl system and we have the benzyl system. The allyl system is a system where you have a double bond and a single bond. Okay, so it's the CH3, CH2. Allyl systems are very common and they are also very very reactive. The benzyl system is the phenyl or the benzene group and the methyl. Okay? Now, you can see that this methyl here is not a CH3, it's a CH2. Because we are speaking about the radical. Okay? So that's all it is. For the carbon to actually have a p orbital, free p orbital, that means that you need to have a hydrogen lost. So that's either by losing a proton, so it would be negative charge, or by losing an electron. So you have a resonance form. You have a radical. Now, so how can you actually get to where you can actually get with a benzylic halogenation, benzylic hydrogen? So this is something that we have done in the past. Okay, it's something to note with the benzene group. It's something the free radical substitution. Free radical substitutions are one of the easiest reactions that you have learned beginning of A level. But if you had to ask why is it that the methyl group reacts faster than if it is with the benzene ring, and this is the reason. So the methyl group will actually will not require any catalyst. Why? Because it's a radical, and that radical can then be transferred throughout the ring. This transfer throughout the ring is very, very important, because that means that you can actually stop the reaction somewhere on the ring. Okay? The radicals are active intermediates, and you can use this to your advantage. Anytime you have an intermediate, anytime you have a resonance form, that is where mechanisms get interesting. Because as we discussed last time, it is these resonance forms, it is these intermediates that will actually take part in the reaction. They will actually take part in the mechanism. Knowing the different resonance forms, you can actually see how the electrons will travel. Now, if you were to look at the benzylic halogenation, the first step is the propagation steps are probably something that you are very common with. You might never have done them for methyl benzene, but these are the same thing. But look at the transfer of electrons. You are transferring radicals. This is something I think we've never done together for sure. Not entirely sure if you've done it with some other teachers. But you are transferring an electron. So remember, it is a single arrowhead. Okay? It's a single arrowhead. Remember, a single arrowhead means one electron being transferred. Two arrowheads mean two electrons being transferred. So, apart from having a benzylic radical, you can have a benzylic cation. So, what is a benzylic cation? A benzylic cation is something where you have a positive charge being moved around. Again, to get a benzylic cation, it's not the simplest thing. You actually need to have a very good leaving group. For example, a good leaving group, such as the sulfonate, would work, and that would end up having a positive charge on the carbon. Now, this is not a very common occurrence. Positive charge on a carbon when you have a benzene ring is not very, very common, but it can exist. Now, again, this is going to be the more stable conformation because it is an octet of electrons, it has octets. So this cation is actually stable because of this resonance form. Without this resonance form, it would be more difficult to make this cation than if it didn't exist. Okay? Which means that Whilst you need to have an electron pushing group to actually give the electrons, it's actually aiding, the same electron pushing group is aiding because there's an oxygen, and the oxygen can get the positive charge on itself, which means that the oxygen is also an octet, and all the other carbons have 8 electrons. Remember, while you don't have to follow the octet rule, in chemistry, the octet rule, whilst it's highly regarded, doesn't have to be followed always, especially in inorganic chemistry. When it comes to organic chemistry, the octet rule is a pivot. If you have 8 electrons, you're going to be more stable. If you're going to be more stable, you're going to last for longer. Now, SN2, when you have a mechanism like this, would then be accelerated, because that means that you can lose the bromine easier. Now, here you have a 100 times faster reaction. What does it 100 times faster reaction? It means that if you had this mechanism, so if you had a mixture of the bromomethylbenzene or bromomethane, you would form 100 benzylic nitriles against 1 nitromethane, nitrile methane, or methanonitrile. This is huge because this delocalization is enabling your molecule to react faster. So it is a very big deal. Why? Because the transition state is being delocalized. So we tend to look at things as static. Here you have to look at the intermediates. The intermediates are what's going to make your reaction faster, slower, more stable, less stable. Remember, when you have the energy diagram, lowering the transition state, lowering your peak, lowers your excitation energy. And that makes your reactions go quicker, that makes your reaction more possible. Remember, by lowering the transition state, by lowering your excitation energy, you might end up in a position where you are also favoring the backwards reaction. But we'll leave that for another day. But for now, just note that lowering the transition state is important because it makes the reaction go faster. So, acidity. When you have benzylic hydrogens, it will not really change the way the acidity of the hydrogen itself. So look, you have pKa of 4 to 1, pKa of approximately 40, that is very similar. Yes, the charge would be separated. Yes, they are still going to have a charge separation over the ring, but it doesn't make a big difference. Okay? The values are relatively simple to that of a normal alkene. This is mainly because even a normal alkene would have some delocalization. Again, this would be a bit higher than an alkane. It would be a bit higher than an alkane. So that would be important. In fact, the fact that it's a bit higher than an alkane, you can use an alkane salt as a base to the protonate. Okay, so methylbenzene is a stronger acid than butane, which means that the butane salt, butyllithium, can actually deprotonate methylbenzene to form the benzylithium group. Okay, these are highly reactive, so normally we don't really enjoy using these in a lab, but if you do, Remember, these are flammable compounds. You have to use them in inert atmospheres, and you have to make sure that you are in safe conditions and safe environments. So, this is one of the reactions that has always impressed me. Why? Scusami. Why? Because this reaction gives you the same product no matter what side group you've got. Now, this is an oxidation reduction. What is an oxidation reaction? Okay, so you can have a system where you have butyl group or methyl or any other group you want, and you can oxidize it to the carboxylic acid. This reaction works, and it works all the time. So, how does it happen? The way it happens is that you introduce a hydroxyl group on the benzylic hydrogen. Once you introduce the hydroxyl group, you can then oxidize it, and once you oxidize, you can get the ketone. Now, the next step is tautomerization. So from the ketone to the alcohol, or alkene and alcohol, the enol, it's tautomerization. So what does this mean? This means that you can now oxidize using KMnO4 to a full acid. Remember, under acidic conditions, this becomes much more oxidizing, okay, and this can cleave the bonds, where you will get the COOH. Of course, for the CH3, it's a similar story, but it's just a bit easier. Now, this reaction is actually something very important. So, anyone who actually needs to continue and further their studies in organic chemistry need to know that you have position-specific reactions. What are these type of reactions? So let's say you have two alcohol groups. Okay? Can you oxidize one without oxidizing the other? Now, normally, students would tell you, of course you can't. If you oxidize one, the conditions to oxidize the terminal alcohol are going to be the same as the conditions to oxidize the internal alcohol. The truth is that is not true. The truth is that you can, of course, oxidize whichever position you want by using the right catalyst. So, in this case, you have, if you use MnO2 and acetone, it will only oxidize the internal alcohol. Why? Because it is the benzylic alcohol. A very interesting case is the case of limonene. Limonene has 3 different alkenes, and you can oxidize whichever one you want using different groups. This is oxidation of one particular site, and it is very important. It is very useful, where you can literally know that your reaction will work on one site and not on another. If you can do this, you can devise synthetic pathways where you can go from one place to another and yet leave functional groups unchanged. even if they are the same functional group. Okay? Even if you have two OH groups, you can oxidize one and not the other. Then you can protect, do whatever you want. Remember, sometimes some reactions have a lot of steps simply because you need to deprotect and protect. So what is a protecting group? Let's say I have an alcohol and I want this alcohol to remain unchanged. So I can protect that alcohol and form an ether. Alcohols are reactive, ethers are not. After the reaction, I will hydrolyze the ether and I get the alcohol back. Now, for benzylic ethers, I can go one further. For benzylic ethers, I can actually get the alkyl chain again. Okay? How? By adding hydrogen with palladium carbon. So, benzylic ethers, I can actually react a bit more. Okay? So, this is crucial. This is very, very, very important. Okay? These two reactions, keep them in mind, because these two reactions are reactions where they will help you a lot. Phenol. Now, today's lesson is all about phenol. So you might tell me, why did we just spend the last 20 minutes speaking about benzylic groups? Because these are related. Okay? The resonance forms are related. And because they are related, then that is why we start doing certain things over and over and over again. We repeat not to make life boring, we repeat to make things interesting and understandable. So, cyclohexadienone is not something you will actually find in real life. The reason for this is that phenol is a much more stable tautomer, and yes, phenol is an enol, which means that it has its own keto-enol structure. Now, of course, the tautomerization process of here, look at the equilibrium constant. It's huge, which means it is shifted to just one side. Now, phenol can polymerize, and this slight equilibrium plays a role. For now, let's actually forget it though, okay? That polymerization reaction. Now, you have the shift of the electrons going from the oxygen towards the ring, okay? This is actually why you will get a slight acidic nature of phenol, because you can actually get the electrons on the oxygen towards the ring, which will stabilize your structure. Okay? How do you name phenols? You have 4 examples. You have 4-methylphenol, 4-chlorotrinitrophenol, 3-hydroxybenzoic acid. So the first 2, phenol is the main functional group. The third one, phenol, is a secondary group. So carboxy group has higher priority. Okay? Hydroxy group has a higher priority. Now, hydroquinones are actually quite interesting, quite important, but look at the name. These are not phenols anymore. Okay? These are not phenols anymore. This is 1,4-benzene diol. So, ethers, you have methoxybenzenosol. This smells really, really nice. The smell of anisette. And you have the phenoxy group. Okay? Now, if you want to look at natural products, and normally we do start going on to natural products, you have 4,4-hydroxyphenyl 2-butanone. This is flavor of raspberries. And this one is the active ingredient in hot pepper. It's called capsaicin. And I'm not even going to ask to do the name. Maybe I can ask you to name it in an exam. Don't worry, I'm just kidding here. These would be complicated names. Okay? You have an amide group, you have an alkene, you have an ether, you have a phenol. So don't worry. This is doable, but it's quite difficult. But as you can see here, it's butanone, 1, 2, 3, 4. It's 2-butanone. Then it's on number 4, on position number 4, it's connected to a hydroxyphenyl group. Again on the position number 4. So it's 4,4-hydroxyphenyl 2-butanone. This is a bit more difficult, but if you want, you can do something similar. You have the alkyl chain and alkyl chain for the amides, but probably it's not worth trying to do, okay? Because it's a bit too complicated. This just gives you confusion. Acidity. So when speaking about benzylic, the benzyl methylbenzene, the benzyl group, it has an acidity of around pKa of 41. Here we have a pKa of 10. So that's a 30 jump, 10 to the power of 30 jump. It's a stronger acid. In fact, phenols will change or might have an indication on universal indicator, especially if you have substituents, okay, like the nitro group, giving and pushing electrons into the ring. If you have electrodonating groups, then it will make the phenol more acidic. Now, why is this the case? It's the case because if you have a negative charge on the phenol, if you have phenoxide, the phenoxide can then go over the ring. Similar to when you have the nitro group, it will also go towards the ring. Okay? Now, this will also be true with other phenols, but it's not gonna be as strong. The nitro group is quite a special group, okay? The nitro group is very, very special, as in the nitro group can actually share its charge. So, a trinitrophenol, you have a pKa of 0.25, which means that picric acid is actually quite a good acid. Unfortunately, picric acid, you can't leave it to dry, otherwise it will explode. I believe one of the first practicals I had when I was a student used picric acid. And there was panic because someone left a few milligrams of picric acid on the bench. Of course, a few milligrams will not do anything. A few milligrams might do a small pop and they're gone. Now, doesn't mean don't take proper care, but remember, everything has its proportion. So don't be too hasty in saying, oh my god, this is a problem. Now, how do we prepare phenols? So, phenols, you can't just prepare them using electrophilic substitution. Mainly because OH plus is not possible. You have never seen a positive hydroxyl group. Now, if you have never seen a positive hydroxyl group, what does that mean? It means that you can't fuse it for an electrophilic aromatic substitution. Now, one of the lessons we had missed was the actual nucleophilic aromatic substitution. I have the lesson prepared, I have the lesson planned. We will be doing it, but its usefulness is in conjunction with this chapter. So we can the plan was to do it a bit after now. Okay, so we can continue doing our syllabus, we can continue learning without the need to revert back to what we missed around 3-4 weeks ago. Now, as students, you are being very helpful. I do understand this is a very stressful time for you, especially because you don't know if you're going to have exams, and that means you don't know what's going to happen for next year. Don't worry, okay? Somehow I'll give you a mark. Maybe I give you a mark depending on attendance here, but we'll see. Now, you can substitute a halogen, for example, with an OH group. It's not easy, it's possible. We'll do them in a little bit more detail later on, and we'll do them as soon as we finish phenols before we start the polyaromatic. So, there are 4 mechanistic scenarios that exist that can take place. Okay? The first one is electron withdrawing groups are present, therefore nucleophilic aromatic addition elimination takes place. This is actually what happens in a number of contexts. If you remember, one of the preparations for phenol at A11 was 200 atmospheres, 200 degrees Celsius for chlorobenzene. This is something similar to what's happening there. You are giving enough energy for a nucleophile to go next to the benzene ring and react. Without electron withdrawing groups, harsh conditions enforce an elimination addition sequence through reactive benzene intermediate. So 1 and 2 are the same. What you're saying is that you can either do it with withdrawing groups or else with energy. Both will work. Sometimes different methods for the same thing will probably work. Okay? You can use something like nitrogen, phenylcation, so the diazonium salts, and then there is the Nobel winning palladium. Okay? Reaction. So, what do you do? The catalyst will help you substitute your chlorine to get either an alcohol or an amine. Remember, both of these groups are not actually electrophilic. So normally, to get to the amine, you need to do what? To get to the amine, you need to actually use the nitro group, and then you actually reduce. But this is a good position. This is a possibility how you can actually add the amine after you add the nitrose without having to change your whole route. So, what's the mechanism here? Important, you need the nitro groups because the nitro groups are electron donating. Okay? Not just electron donating. Nitro groups are very special because they allow for resonance structures and resonance forms to form. Okay? So, the nucleophile will actually open up and add like normal nucleophilic substitution, okay, SN2. But this time around, instead of eliminating the chlorine, it breaks the localization, with the negative charge being resonated through the molecule. Okay? This is why you need possibly two. The meta nitro group will not work because there will not be a resonance form there. Okay? If there's no resonance form, its position is useless. And then you can eliminate. Of course, this elimination, whilst you're seeing it from the nitro group, can happen from the other side as well. But this elimination is only possible because there's a resonance form that's supporting that negative charge. We see the last step, but normally it's not just one step, okay? Second case, benzene mechanism. So the first one was when you have electron withdrawing groups. Case 2, when you have the benzene mechanism. So, just a reminder, we are speaking about these 4 cases, okay? So, this is the substitution for a chlorobenzene. High conditions. They're normally done at a level, I think 200 and 200, but doesn't really matter. Still high conditions. Or you're using NH2 and NH3 as an acid. Remember, NH3 is a base, so to actually lose the hydrogen, that's gonna be something huge. Okay, so KNH2 is actually a very strong base. And then you add water. These 2 reactions are possible. You might want to know them, but they are highly unlikely to ever be used in one of your labs. Now, how do you know the mechanism for the reaction? A mechanism, because if you have a carbon 14 label, then you see that it was 50-50 with regards to your products. We're gonna do the benzene mechanism soon. Benzene is when you have a triple bond on one of the benzene positions. Okay, so having a double bond, one of them would be a triple bond, but we'll speak about this later on. Okay, we'll speak about this, I believe it will be next week. So what happens here? You get your very strong base to the protonate. Now this is pK of 44, so you can imagine the type of base you will need. Okay, but once you get that base, then you can remove a hydrogen, which can then kick out the chlorine to form benzene. Once you form benzene, then you can do normal addition. So it's an important reaction, and I would recommend that you know the mechanism, but it's highly unlikely that you will ever use this in one of your labs. Diazonium salts. This is a super leaving group because nitrogen wants to be released, and therefore it's going to be very easy and very energetically favored. Okay, so this is probably one of the easiest ways how to actually make and get your products. Or you have a palladium catalyst reaction. This is the way to go now. So nowadays we use catalysts, okay? Instead of heating, you use catalysts. This is like dating. Instead of actually trying to talk to a girl, talk to a boy, you offer them a drink. Why? So their inhibitions are lower and they might like you. Same thing goes with chemistry. Chemistry, instead of wasting your energy trying to heat things up, you can use a catalyst to find different routes. Palladium catalysis is increasing in popularity. Unfortunately, we don't have much palladium, but palladium catalysts are increasing, and palladium catalysts are something that we actually might need. Okay? So, you can either add the alcohol. If you want, you can add amines. They will work as well. So, these are new ways how to actually get to these positions. Now, I don't want to bore you with a lot of detail, but these reactions are useful. These reactions will save you lots and lots of time. So, the mechanism here, the palladium forms a bond between the halogen and the benzene ring. It forms, and then the palladium halogen bond can be changed with the alcohol, which can then react with the benzene. Now, this is a simplified version, okay? The phosphine ligands are important, so you have the PR3 here. Different PR3 groups would actually have different reactivities, so I don't really want to go into the mechanism myself. I've studied this reaction. It's a very, very interesting reaction. If you do want more information, please don't hesitate to tell me. But for all intents and purposes of what you need to know, this is not relevant. Okay? Chemistry of phenols. Basicity of phenols is weak. pKa values of methyl and phenyloxonium ions is around minus 2.2. So that means they are weak bases, okay, because they want to lose that proton. Actually, the protonated versions of phenols, they are actually strong acids, okay, because phenol is stable. Phenol doesn't want to lose or gain hydrogens, meaning that the phenoxide is a strong base and the protonated phenol is a strong acid. Okay? And you can't have phenylcations. So, whilst water is a very, very, very strong and good leaving group, you cannot lose water from phenol. Okay? Which means you cannot form a phenylcation. Remember, in reality, this would not be aromatic then, I believe. I think it would be quite unstable, but I can't, at the moment I would have to work it out. But phenol itself is a leaving group, which means that if you have an ether, phenol is a leaving group, okay? And one of the way phenols can react is they can also act as nucleophiles. So the Williamson synthesis, something that you've done at A level, is actually a nucleophilic addition. So phenol acts as a nucleophile over or against the halogen alkane. So Williamson synthesis, it follows SN2 or SN1 mechanism depending on the halogen alkane. It's something you should know, okay? This is something that is very, very important. Phenols can form esters, but phenols cannot form esters with carboxylic acids. It's very difficult. So normally you use things like acid chlorides or aceton hydrides. They are much more reactive, and that reaction will actually happen a lot quicker. This is in fact salicylic acid or 2-hydroxybenzoic acid is used to prepare aspirin. Aspirin is something that I think we've all used in the past, something very cheap, very easy to make, and it's an ester of phenol. Now, very important, if you have an amine group, amines are more nucleophilic than phenols, okay? Which means that your aceton hydride will first react with your amine, and when this has all reacted, it will then react with your phenol group. Now, electrophilic aromatic substitution. As we said, phenol activates the ring. What does it mean that it activates the ring? It means that phenol activates the 2 position and the 4 position. Nitration here, you end up getting more the para products than you get the ortho products, mainly because of steric repulsion or electronic repulsion here. In both cases, okay? Halogenation is fast, does not need a catalyst, and if you want to only get the monobromination, you need to cool it down. A lot of students forget this. A lot of students think that you can never get the monobromination. Of course you can. It all depends on the conditions. Why does this happen? It happens because the hydroxyl group, or the phenol here, is activating, and therefore the ring can react without having a very electrophilic bromine. Now, CO2 can also react, okay? And this is a way how to make the salicylic acid, and this is a way why aspirin is so cheap. Now, having said this, the Kolbe-Schmidt reaction, it's not the easiest of reactions, okay? But consider this as literally an electrophilic addition. It's an electrophilic addition where your electrophile is carbon dioxide. So, now we're going to speak about 2 mechanisms, the Claisen rearrangement and, the Claisen rearrangement and the Cope rearrangement. Okay. So what is the Claisen rearrangement? The Claisen rearrangement is an extension of electrocyclic reactions, okay? And where you are moving and you are preparing a phenol from an ether. Now, you need to have the right structure. So you need to have a oxygen, carbon, carbon, hydrogen. So the benzene group here has to be open like that. And you need to have oxygen, carbon, carbon, double bond, carbon. So without this position, the Claisen rearrangement will not work. Once you heat it up, you have a concerted process where you form a ketone, you form a new bond, okay, and you form a new alkene. So you have a terminal alkene to result in a terminal alkene. Of course, as discussed before, we need to have tautomerization here to form the phenol. This is a 6-electron step, 6-electron concerted process. This is why you need to have the right conformation, because otherwise you will not have the right shape. You can see here you have a ring, okay? It's not joined together, but they have to be in the right position. Of course, this can happen with the carbon analog, which is called the Cope rearrangement. So, this is the Cope rearrangement. It's something very, very similar where you have 3 double bonds all moving around, or you can have single bonds breaking, forming new compounds. This is an important reaction, the Cope rearrangement. We'll be studying it later on, I believe. No, not really. We've done different reaction. This time we've done the Cope elimination. I believe this reaction you should have done either in first year or in second year. And this is other uses of the Cope rearrangement or the Claisen rearrangement, whichever one you feel more comfortable with. Remember, the Claisen rearrangement is supposed to form the phenol, okay? Not to do anything else. But follow the mechanisms and you should be fine. Follow the arrows and you should be fine. Again, these are quite complicated analogues. I don't really want to go into them because you just need to know how to read them. At this point, I want you to learn how to read the mechanism. Okay? Now, this is all there is with regards to phenols. If you look at the syllabus, you've got something about bakelite formation. Bakelite formation is a polymer, and we'll be discussing it later on. Okay? We'll be discussing it at a later stage. For today, I bid you farewell. I will stop the lecture here. We are doing a lot of work online. In reality, I used to go around 15 slides per hour in class, which means that I used to skip a lot also, but I used to do around 15 slides per hour. I will not be burdening you with a lot more work because we're not in class and I can't see your face, I can't ask you questions. So I'd rather have a bit or a much shorter lecture and you go and work, you go and study. By 11 today, I'm going to actually go and send you a few questions. The questions aren't compulsory to do them for next week. But if I were you, I would practice for my exams as if I have the exams anyway. I don't know what's going to happen. I talked to Professor Sinagra. He's not sure as well. I think this is something that needs to be discussed later on this month or early next month. Stay safe. I was sick this week. It wasn't corona because I was tested. But so that's good for you because I had seen you in the last 15 days. But it was just the normal common flu. Stay safe. because illnesses at this time of year are very common. You don't. The worst thing that can happen to you is not to get corona; it's to get two illnesses on top of each other, and that's when complications can arise. So, stay safe. Take care of each other. If you need anything, just ask. Thank you. Have a nice day and have a nice week. What? So, as far as I'm concerned, even if you were to have the exams, I can't use your practical reports because not everyone has done them. But if I were you, I would do everything as normal. So if you have deadlines, abide by them. We don't know how long this will last. So let's say after Easter, we can all go back to university. Let's say after the 21st, instead of having a lecture here, I see you at university. Okay? What that means is that life goes on. I think it's unlikely that in 4 weeks' time we'd be out of this turmoil, but life goes on. So just prepare everything as it should be so that there will be no problems. With regards to practical reports themselves, they're online. So I think you should just submit them online as usual. With regards to doing new practicals, wait. Okay? Let's see what happens. And once we see what happens, then you can think about it. In my opinion, I will treat everyone as equal. I think that practicals have a bit more marks than you get in the papers. It's easier to get an 8 in a practical than in an exam. So everyone has to be treated the same way, which means that everyone has to have the same chance of getting the same grades. So if not all of you have done the practicals, again, because of what's happening, then that's a different story, okay? We have to know that. It should be. Thank you for letting me know there. Let me take a look into it. So the practicals, who would normally correct them then? Is it the lecturer or your invigilator, demonstrator? I look into it because, as far as I'm concerned, from my side, it's open. I'll look into it, okay? I'll let you know on the group. This could be a system where I don't know what could have happened actually, because it doesn't make sense that it's not open. I'll look into it, okay? For now, I'll I'll end this chat. I'll end this live stream. Speak to me on the Facebook group if you need anything with regards to VLE. Let me take a look into it, because I know that the VLEs I have for my teaching course, we had some troubles because they were opened late as well. But they've been open for a while now. So let me take a look into it and see what happens. Okay? Have a nice day, guys. If you need anything, just ask.